Quantum field theory unification of the electromagnetic and weak forces require it, and electroweak was experimentally confirmed. So it was, the Higgs boson was a very strong prediction of the standard model of particle physics. If we didn't find it, it would have meant we had found a problem with the standard model of particle physics. Now, there is also a consequence that mass, the fact that particles have mass, results from interaction with the Higgs field in a way that I don't really understand, and here's the flowchart for understanding the Higgs mechanism. I'll let you ponder this for a moment. So there's this problem that the Higgs mechanism is really complicated quantum field theory, that you have to understand a lot of quantum field theory to understand what's going on. Now, you can find a lot of popular descriptions that attempt to be analogies that describe the Higgs boson, how the Higgs boson, and it's not even really the Higgs boson, it's the Higgs field, not the Higgs boson itself, how the Higgs field gives particles mass. And then you hear analogies like popular people walking through a crowded room and other people come and hang out around the popular person and that slows them down as they're moving through, and all of these. And I have to admit, those analogies have always left me a little cold, and the main reason was, I use popular analogies all the time to try and help understand science, and I think it can be great, and they can be extremely useful in figuring out what's going on. But the problem is with all these fields is I had no idea how that actually connected to the underlying physics and what they were really trying to tell me, and so that always left me a little bit cold. So here's how it really works. And that is the fundamental equations of particle physics, the equations that we use, that physicists use to describe how they interact with each other. One way of formulating those equations has a whole bunch of energy terms in them that you add and subtract in the right way. And so you could do, and you'll write this down for any given field. So if you're doing an electromagnetic field or the electron field, you write down all the various terms that go into these things. You call it the Lagrangian. You write down one of these equations. And so all those fundamental terms have energy terms, and there'll be terms that correspond to equivalently the kinetic energy of a moving particle, and things like that. There are also terms that correspond to the interaction of fields with other fields. When they interact with each other, energy can arise in that interaction. Now, there is this problem, though, is that some particles have mass, including the W and Z bosons, and so you had to add an extra term, almost sort of ad hoc. You just had to add a mass term to those equations to make it all work out. And it was sort of, well, why add the mass term, and why does it have the value that it does? Well, because we need to, was really sort of what it came down to. And so you have all of these energy terms. Well, the way the Higgs mechanism works is, if you muck with your equations in just the right way to do the electroweak symmetry, so that when you put together the equations that make the electroweak symmetry, they say, okay, well, you need to have another field. Another field gets produced by the making of this symmetry. Oh, wait, we'll call that the Higgs field.